we'll move on and talk about the ex situ prototype test, because I can see the time is ticking away here on me. Let's talk about ex situ application of STAR. So here's the basic concept, and we're going to use a demonstration of the basic concept, something we did. We did this demonstration about 5 years ago now. We did it on the cheap with some research budget. This is before any big companies were involved. And we basically took a skip, or what you call a garbage dumpster, and filled it with contaminated soil, and basically ran a large column experiment inside that dumpster. And so just like with everything else you've seen, we do ignition along the bottom, and we get this upward propagation of the reaction front. That's the idea. And hopefully clean up a whole skip full of contaminated soil. So this is the experiment we did in Glasgow on the order of, I gotta say, on the order of 5 years ago. And we purposely mixed coal tar with clean sand to create a mixed contaminated soil to our own description. And here's a plan view of the air distribution radial pipes, and the igniters were located in these 4 quadrants on top of these pipes. Here's a side view, and basically this is what it looks like. This is a photograph of what it looked like before we did the test, and this is a photograph of what it looked like. It took us about 15 hours to have the reaction propagate up through this zone. It was about 1 meter tall, and it took about 12 hours for it to cool down before we could excavate it. And we got a very typical results, again, on the order of 31,000 milligrams per kilogram before, and pretty much clean sand afterwards. You can see, again, this sand had a sort of a reddish tinge to it afterwards because of the iron oxide in the sand. So very, very encouraging. And it was this kind of result that allowed us to work with a major oil company to develop a prototype ex situ reactor, because, as I said, they have these tank bottoms that they want to treat. Now, the tank bottoms themselves are not a soil. They have a bit of silt and grit in them from the reservoirs where the oil's been pumped out of, but mostly it's just liquid. So it's already on the surface, it's already excavated, sitting inside a lagoon or in a pile, and what they need to do is, what we want to do is mix it with sand, treat it in a reactor, get the clean sand back out, and reuse the sand over and over again, mixing it with the sludge and treating it over and over again for very little cost. So basically, here's what the system looks like. It's basically an igniter that we use during ignition only. The front travels up, it gets clean, it gets dumped out, and it gets done over and over again. We're also working on a continuous system that could be treated. The reaction would continuously be in here. We keep feeding in fuel from the top, and the reaction would stay inside the reactor. But for the moment, we're starting off with a system that is batch. You treat the system in batch. And you can see that we have a extraction system, we analyze the gases, and then we, again, just for total safety, even though we have very few vapors, we still treat them with activated carbon and then release the clean air. So this is what it looks like. This is, we've built this over the last year and a half. It's in London, Ontario here, at one of our research facilities. We've partnered up with this company, GTI. They've been fantastic partners. They're experts at fabricating reaction vessels, basically. This is a 3 meter tall, 1 meter diameter version of our column experiments. It has a very nifty mechanism whereby there's a hydraulic mechanism that allows us to take the bottom to come off, to dump out the clean sand. We then put the bottom and the locking ring closes, and then we actually have a sand elevator here. It's basically so we have big buckets of sand, a sand reservoir. It brings the sand up, mixes it with the sludge, and dumps it into the top. So we have a loading system. We have an unloading system. The sand falls down into this bucket here. And we have air. The ignition system is in the base here. We have air being blown up through here and then collected out the top. And these are thermocouples located all throughout the system, so we can track temperatures. And what's very interesting is the entire apparatus, which is several thousand kilograms, is on these very sensitive load cells. So we can track mass loss as a function of time in real time. And basically, this is a pilot scale, so maybe it's on the order of 1/3 real scale. And the idea is to ensure, we know STAR works. We know STAR works for this material from the treatability study. What we don't know is the best way to load, to unload, how long it will take, what the velocities will be, that kind of thing, and how we can optimize the process. And we did, the first 5 tests were with vegetable oil, which is a good surrogate contaminant. And then the next 6 tests were with the actual crude oil sludge. So here's an example of from one of the tests, of what the mass destroyed as a function of time. Now we're not using an indirect measure of CO, CO2. We're using a direct measure of the weight of the reactor as a function of time. So you can see it's basically a linear reaction as the front propagates up the column. We're getting a linear rate of mass destruction. And you can see that the mass destroyed is almost exactly the initial mass added. We basically have nothing left. There's a little bit of sludge that's below the igniter in the reactor, and that's this difference in weight here. Because the treatment, of course, doesn't go down. It only goes up. So there's a little bit of mass left below the igniter, but everything that we tried to treat was completely destroyed. And it took on the order of 35 hours to destroy those almost 350 pounds of sludge. So that's very encouraging. And here's a video of how the temperatures evolved, how the front moved through the reactor as a function of time. This zone down here is a contaminated zone, and this zone is we put half of it, in this test, half of it was contaminated, and half of it was clean sand. So here you can see the reaction starting, the heater's off, and you can see the front moving up, and we see a much thicker front than we did previously. We see a lot of the heat being retained inside the clean sand. So basically we have a very strong reaction propagating up through the soil. You see a strong reaction propagating up through the soil, and then a lot of heat being retained in that clean material at the top. And it very slowly cooling down over the next day or two. And this is what the material looks like. This is the sludge at very high concentration. Of course, we're mixing it ourselves. So we can mix it at any concentration we want. So we pick a very high concentration. And this is what it looks like afterwards. Very, very encouraging. Very similar to our treatability studies. So ex situ STAR is looking very, very good. Of course, there's some advantages over in situ, which is one, you can homogenize the soils and heterogeneity is less of an issue. And of course, it's highly controlled. We can optimize the airflow rate. We can optimize the concentrations as we want them. If it was too fine of a material, we could add a coarser material. We could do whatever we wanted. We see treatment just like the column tests. We see the possibility for treating liquid wastes that we intentionally mix with sand and we recycle the sand. We see that we could have, for example, a treatment center where we mixed really high concentration waste that had lots of excess energy with some low concentration waste. Remember, I mentioned that there's some soil that we can't treat normally because there's not enough fuel there. Well, in this case, we can mix the two of them together, throw them in the reactor at the same time, and therefore treat both at once. And of course, we're also developing, we have design plans for a mobile treatment system that would drive around to different sites. So we could do excavated materials, but not having the excavated material leave the site, which can be a big advantage. And the treatment's so thorough that some of the soil we've done has been classified as being good enough to be put back into the ground, which for most technologies, you could never do that. Even after you treat it, you still have to send it to landfill because it hasn't been treated enough. And if you're trying to, for example, bioremediate petroleum hydrocarbons, that's a typical result. You knock it down a lot, but you don't knock it down enough to reuse it. Okay, so that's the end of that section. I'm just going to check to see if there's been any questions. The question I have here is, it says, first of all, the comment, that's incredible. Forget in situ and just do ex situ. That's the first comment. I agree that the ex situ looks very promising. But you have to understand, as I showed you in the sustainability analysis, excavating all soils, first of all, incredibly expensive in terms of energy. Second of all, it's hazardous. You're bringing hazardous material up to the surface where it can volatilize, get in contact with people. You know, in many sites, first of all, it's either too deep, or it's too expensive, or it's too hazardous to, bring the material to the surface. So in situ has a lot of advantages. Of course, there's challenges in terms of the in situ heterogeneity and things like that. But in many cases, in situ treatment is an important alternative. So thanks, though. And the other question was, could you potentially sell the clean fill? Oh, I think I've answered that. Yes. In this case, the material is so clean that basically there's a lot of potential for putting it back into the site, using it as fill on a development site. It's even been classified as clean enough for fill into harbor development projects where you need to put things into the lake. So those are all possibilities. The one issue that should be brought up is that it has no organic material in it whatsoever. So for people who are concerned about the viability of the soil as a growing medium, and that can be important if it's a superficial soil, like a potting soil, then you have to understand that you're not just destroying all of the, like any thermal technology, you're not just destroying the contaminant, you're destroying all the organic carbon. So the organic carbon is lost. And so it becomes sterile. You also lose all of the natural organisms that exist there. Now, we have been doing some tests in the lab that show that if we add some groundwater, natural groundwater, or we mix it in with like 10% compost, the soil quickly regains a lot of its viability, and we can grow plants in it. So it's not like it's lost forever, but it is temporarily a relatively inert material. So that's a function, something to keep in mind. And now, if you're doing in situ and it's at depth, it probably doesn't matter too much whether it's relatively inert. Groundwater is going to flow back in there anyway, and it's not, you don't have a lot of roots down there and natural organisms that are doing a lot of, near-surface ecosystem activity. But as a surface treatment, that's something to consider. All right, thanks for those great questions. All right, volatile contaminants. Now, I told you that normally we can't do STAR on things such as trichloroethylene because it's volatile and has a very low boiling point. But in fact, so here, for example, here's a thermocouple profile. You should know what these look like now, temperature versus time, of neat TCE DNAPL. And what we see is we do get some ignition here, but we get these sort of decreasing peaks and the reaction sort of dies out. It's not self-sustaining, and that's because a lot of the mass is being volatilized ahead of the front, and when the front arrives, there's hardly any fuel there. So what we've looked at is that we know already that in a lot of sites where there's chlorinated solvents, we typically inject vegetable oil. And we check vegetable oil as a organic substrate donor for aggressive bioremediation. And we know that vegetable oil has a lot of calories, a lot of energy, and it can mix with the DNAPL very effectively. That they coalesce into a single phase. And here's the energy content of various fuels. You can see that propane and diesel and wood have fairly high energy content, just like vegetable oil, whereas TCE itself has energy. It can be combusted. It's often incinerated, for example, if it's in an ex situ treatment system, but it doesn't have a lot of its own energy. So we did a whole suite of experiments where we basically looked at whether we could use vegetable oil as a surrogate fuel for destroying VOCs or remediating VOCs. And we looked at all of these factors. So this is what happens when you take TCE at 10% of the pore space saturation and mix it with 15% saturation of canola oil. And you see now we're getting a very nice self-sustaining front. Peak temperature about 550 degrees. Very nice self-sustaining front. And here's we used a oil blue dye. So this is what the TCE, this is the blue dye TCE before and after. So basically we know that there's no TCE left. There's no vegetable oil left either. And we did a whole bunch of different oils, and we saw that canola, sunflower, and peanut oil all were very, very promising, strong self-sustaining reactions. Soybean oil, olive oil, and corn oil, they had the potential, but at the scale that we were studying them, we couldn't say they were completely self-sustaining. We would need a larger scale test to know for sure. We also did a biofuel, methyl soyate, In that case, it was really not self-sustaining at all. So I can't tell you why. These all have very similar chemical formulas. So it's hard for me to tell you. I don't know yet why some are better than others. We just know that it's true. Now, what's the fate of the TCE? Here you can see that the initial experiment here, one of our base cases, 10% TCE, 50% oil, had 1.3 moles of TCE in it, and this is the mass balance. We measured the TCE in every phase. We basically got 1 mole of TCE being volatilized ahead of the front. At the end of the day, 0 moles of TCE was found in the soil. It was completely clean. There was a very small amount of gaseous PCE, because PCE, you should know that if you incinerate TCE, sometimes one of the byproducts is PCE. So we're measuring now PCE, even though we didn't actually add any PCE. Very little bit is being generated in the thermal breakdown of the TCE. And we also measure for phosgene. Now, phosgene is a chlorinated toxic gas of significant concern whenever you're incinerating TCE. So we measured very carefully for phosgene, and we saw incredibly small amounts, much, much less than the regulatory limits of phosgene. So that's promising. Now here's a whole bunch of experiments that shows very similar results. So we did some with more TCE, with less TCE. We did a whole bunch of experiments, and basically none of them had TCE left in the end. And all the results were very similar. Very little PCE generated, a significant fraction emitted as TCE, and the rest of it being combusted. So if we look at it on a graph, we can see that in every case we remediated the soil, about 3/4 of that TCE was being volatilized, and about 1/4 of it was being destroyed. A tiny bit was being emitted as PCE. So on one hand you might think that's disappointing, that we like to, because STAR was so successful with destroying with very little emissions for the coal tars and creosotes, crude oils. But the truth is, this still has a strong potential. Other ways that we treat TCE in apple is, for example, volatilization, either through thermal, which means injecting a large amount of energy into the soil for maybe 6 months and volatilizing all of it. Or, so you're trying to heat up the entire site at once to maybe 100 degrees. Or you're doing air sparging and purposely volatilize. So there's a lot of ways of transferring TCE to the gas phase. And this just might be a very cost-effective way of doing that. And destroying some of it in the process. Here, now, we looked both at neat oil, and we also, of course, looked at emulsified vegetable oil, because when you inject oil into the ground, if you want to get a good radius of influence around your injection well, you often inject emulsified oil, which is basically droplets of oil encapsulated inside water, so that you can push those droplets further away. So we did it with EVO and TCE, and we had equally good success, which is promising. And here we did, now in this case, we're pre-mixing the EVO, the TCE, and the soil. In this case, what we did, we took a clean sand column, and we injected vegetable oil. And we also injected TCE. So we injected TCE first, and then drained it to residual. Then we injected vegetable oil, and then drained it out as well. And then we did the reaction. So we're trying to do things closer to what would happen in the field. And what you see is this sort of, we don't have nearly as nice set of curves, because there is some heterogeneity. There's some places that are more packed than others. There's some places that have more fuel than others, some more oil than others. But what we see is basically the reaction does propagate through the entire column. Remember, these thermocouples are only on the center line. So it could be moving in a kind of heterogeneous fashion. But in the end, the entire column was completely clean, and there was nothing left in terms of oil or TCE. So we do see that there's good potential for remediating any kind of volatiles using vegetable oil as a supplementary fuel. Certain really cheap and food grade oil. I mean, whenever you want to inject something to the surface, it's nice to inject something that's food grade and has no toxic implications. It's also likely that any oil that you don't smolder will probably support ongoing bioremediation. So we're looking at that now as well, coupling STAR with bioremediation. We saw that there is a minimum of oil that you would need. So, for example, we needed at least 14,000 milligrams per kilogram of oil to destroy 8,000 and upwards milligrams per kilogram of TCE NAPL. But 3/4 we were volatilizing, 1/4 destroying, and everything was totally clean afterwards. So there is some potential there. Whereas a few years ago, if you asked me, I would have said that there was no potential for volatile fuels. So that is encouraging. And I'm on the last section. I'm just going to check for any questions before I go to the last section. Okay, there's a question here. Is there a risk of volatilized DNAPL transferring to the dissolved phase groundwater as it contacts the cooler groundwater on the fringes of the treatment area? And so yes, that is true. If you were doing treatment at depth, then you can have some of the gas phase partition into the groundwater and have, now probably if you're dealing with a TCE contaminated site, probably that groundwater already has TCE in it. So I'm not sure if you're going to be creating it would be site specific. I'm not sure if you're going to create a groundwater plume where you didn't have one before. As you continue to disparage more and more air, you could also, so you'd have some forward transfer of TCE, let's say, into the groundwater. Then if you continue to put air in, even after the reaction is done, you might have back partitioning out of the groundwater. So, as I said, there might be already TCE in the groundwater, but there is the potential for that. It's not something that we've studied in depth, but it is something definitely to keep in mind and consider. Now, it also depends if you drive off all the water or not, depending on how shallow you do. For example, in our shallow in situ test, the reaction was so strong, it basically dried out that entire cell. And then groundwater flowed back in later, but there was no water between the front and the surface. So that can happen, and in that case, of course, you don't have to worry about contaminating the groundwater. But if you're doing it very deep, then probably you are transferring the hot gas through cooler groundwater, and so that becomes more of a consideration, for sure. So thanks, that was a good question. I want to talk about, we did a lecture in this course already about numerical modeling, so I wanted to talk about numerical modeling. So I wanted to talk about how numerical modeling is informing what we're doing with STAR. And I only have a few minutes left, so I'm not going to spend a lot of time on this, but it's a very useful tool in the development of any technology. It really helps us study things that are otherwise very hard to look at. So I'm just going to mention that we've developed a model, and that model basically couples together a multi-phase flow model, and we haven't talked about that in this course too much, but I'll talk about it briefly in a minute. But a model that can simulate for the flow of different phases through soil. It combines basically an analytical reaction expression, the one I've shown you before for the velocity of the front, as a function of different variables. And it couples these two things to a third different model completely, which is a combustion spread model, which basically is a geometry-based model, which can simulate the spreading of a combustion front, through space and time. So what we're doing in this type of modeling is we're not modeling the detailed physics of the hundreds of reactions that are going inside the front. We have another model where we're trying to do that, but it only works on the scale of centimeters because it's so numerically complex. Here we're trying to make a model that's not as complex, but we can actually use to do field scale simulations. So we're trying to incorporate just what's essential of the processes going on. Now, this is pretty complicated. I don't expect you to learn this whole thing. I just want you to get an idea that we have a multi-phase flow model that basically solves for the movement of the NAPL and the movement of the air. And so at every time step, it solves for the air velocity vectors, the vectors throughout the pore space, where the air is and how fast it's moving, and the concentration of NAPL at that location, essentially. And that's a model I developed during my PhD. Then we feed in the concentration of NAPL at every location and the velocity and direction and magnitude of the air velocity vector. And all of these things and the porosity of that location, it gets fed into this reaction expression, which calculates the velocity of the front, basically. because a lot of these things are constant for give us fuel. And then, oops. Oh, okay. So for a moment, I just want to mention now, this expression has a calibration parameter. So what we did is we took all of the column experiments that we did, and we developed a calibration. So we get a certain velocity of fuel, of contaminant, for a given air flux. So and at each node in the model, you can have a different concentration, and you can have a different air flux, and the model will give you a different velocity. Okay, and that's solved on a node-by-node basis throughout the entire domain. All right. Then, basically, it goes into a module that calculates if it should spread. Because remember I told you if the airflow is too low, there'll be no reaction, so that's what this is. There's an off-on criteria here. And if it's high enough, if it's below the criteria, then the front doesn't spread at all. If it's above the criteria, then we use these values that we calibrated to our two-dimensional experiments, and it creates a front that propagates outwards from the ignition point. And then what it does is it just iterates to basically make a nice smooth front, and then it removes instantaneously all of the NAPL behind the front. So this is how it's not a true chemistry model. It's not actually doing the stoichiometry of reaction. It's calculating where the front is in space and time, and the movement of that front, and everything behind it is removed for NAPL. But that's really an important step, because when you go back into this time step, then the concentration distribution changes, and that changes the airflow pattern. And that's why I was telling you before, you can't just predict where the airflow is going to go and assume the front's going to go there, because here is a very coupled process. The airflow is very dependent on the NAPL distribution. As you know, hopefully from other courses, when you have lots of NAPL, it's hard for air to flow, and where there's little NAPL, air can flow well, right? And so you can imagine that there's a clean zone through which air is moving very, very well, and the air can propagate from your ignition point right to the front very easily. And then when it reaches the front, of course, it doesn't move through that front as effectively. And so there's a coupling here between the airflow and the NAPL saturation, which is affected by the propagation of the front. And it helps deliver air right to the front. All right. And the nice thing is, I should mention, it also accounts for water saturation. But of course, if there's a dry zone behind the front, then it also allows the air to reach the front very effectively. Okay. So here's the column experiment I showed you way back about 2 hours ago. And here's the propagation of the front up the column in terms of the simulation. Okay, so here's the air velocity vectors that of course, they're uniform. This is a 1D experiment. So the air velocity vectors are going upwards uniformly from the air diffuser at the bottom. And here's how the front is simulated. Here's the igniter at this location. Red here is clean. Blue is contaminated. And here it shows the front propagating upwards as predicted by the model as a function of time until the whole column is clean. It takes about 23 minutes to clean up this column. And that matches very, very well with the experiment. Now, of course it matches well because we calibrated the experiment, the velocity of the front, to the experiment. So it's just encouraging that it matches, but not really revolutionary. Here's an experiment. Now, this is something it's very hard for us to do in the lab. We've taken the same sandbox now, and we've done 3 different permeabilities: a very low permeability material, a high permeability material, and an intermediate one. Okay, because we want to start to study. And now, instead of doing a line source, we've done a point source, because we want to really study how heterogeneity might affect the propagation of the front. So this we don't have any confirmation for. This is a prediction of the model. So first of all, here's the airflow pattern that's predicted at time 0. And as you can see, as you imagine, most of the airflow is channeled through the coarse sand. There's a little airflow going through the fine sand and almost no airflow going through the very, very fine sand. And when we start to ignite, we can see that we get this interesting shape of the smoldering front, and it spreads as a function of the airflow rate. You can see here that it moves fastest upwards, as we would expect, and then more slowly outwards to the side. And as we move forward in time, we can see we've cleaned up all the coarse sand. We're slowly still propagating through this fine sand because there is enough oxygen in there, but we're not cleaning up this very, very fine sand. The airflow velocity is just too low to support a smoldering reaction in there. It's probably getting heated, but the front's not propagating through it. And so at the end of time, you see that this is the final time step. We've cleaned up most of the column, but there is a concern here that we could have regions that get bypassed. Now here's the simulation of the 2D experiment that I showed you before. This is the contaminated material, and we have ignition and airflow at one location. And now we're going to simulate the same experiment that I showed you before. This is just for your reference later. Here's all the various parameters that we use that we take from the literature for the various inputs to the model. These are the thermodynamic properties, and these are the porous media properties. And so here's now the simulation of that front that I showed you for that experiment that we did, the 2D experiment. And we see it mushrooming outwards from the reaction zone. And now it moves very quickly through this phase. But you can imagine that once it hits the top, now most of the air is just going straight upwards and outwards. This is a clean sand up here. So there's really very little resistance. And so the airflow vectors change dramatically between this point when they're pushing out in all directions and this point when they're primarily going upwards. But we still see some outwards lateral propagation, but it slows down and slows down and slows down until eventually the reaction goes extinct. Right here at 56 minutes. The reaction terminates itself. And a lot of the work we spent by my latest graduate student, Tanzir Hassan, was on developing a reaction an extinction mechanism to make sure the model actually extinguished at that point. And what we programmed was that when the airflow vectors are small enough, the reaction will go out. It needs a minimum airflow for it to continue. So now here's the upwards velocity. Remember I told you it was linear in the experiments. That's the circles. Here's the predicted upward velocity. So it's a very, very good match, including the zero velocity when the airflow rate was too low. So this is really encouraging. This is for the 2D experiments. And this is now a comparison. You remember these diamonds and, the triangles, circles, and squares I showed you earlier that we were anticipating where the front is based on where the red circles were? This is the thermal severity criteria. So now we're comparing the simulated results of the model with these experimental results. And we get an extremely, extremely good match. This is the predicted final location of the front and the actual excavated location of the front. So we're getting really good predictions of our 2D experiments, which is really promising. And now we can look at the effect of airflow rate using the model, and we can see, similar to what I showed you before in the experiments, we can see that these propagation fronts as a function of time, first of all, we see it moving very slowly at low airflow rates and very quickly at high airflow rates, and we also see this radius of influence being quite different at the high airflow rates than the low airflow rates. So the modeling is showing us things that we've already learned through the other sections of this lecture. Here is, now, of course, the value, we compare it, and Professor Molson talked about this. Of course, we need to validate or calibrate our models or develop confidence in our models by comparing them to very carefully controlled experiments. But the value of the model, once you've done that, once you have confidence that it's working well, the value is to look at field scale scenarios that you otherwise couldn't. These obviously are experiments. It took us 3 years to do those in situ pilot trials to set everything up, plan it, execute, analyze it. We don't get to do this very often. Whereas now, we can take this model and we can run tons of different scenarios and look at, for example, a single ignition source versus multiple ignition sources. We can look at vertical ignition wells versus horizontal ignition wells. We can do all sorts of things with heterogeneity using the model, which is really encouraging, and this is how we can take the science forward and help design the most effective field scale systems. So here's an example of a scenario that looks remarkably similar to the near-surface pilot test that we ran. We have a well, we have a clay layer, we have a coal tar layer, we have the water table up here, and we have our ignition source, and we're going to do some simulations and look at some sensitivity analysis. You know, I would never say that a model is great for telling you exactly what's going to happen in the field. The field is just too complicated to represent all of that in a model. But what it is good for is looking at how the results might be sensitive to various parameters. So for example, here we're looking at the sensitivity to coal tar saturation. Our base case is 50% of the pore space occupied by coal tar. But we said, well, what if it was only 25%? Or if it was 75%? And here we're going to step through time with the model and look at how the saturation controls the radius of influence over time. So after 126 hours, you can see that we predicted a sort of, in this case, now here we're using a very, very high air injection rate, and but so I'm not sure if this radius of influence is entirely correct, but what we're saying is that the radius of influence will be significantly larger for lower saturations of coal tar, and you can see the kind of sensitivity that we expect. Here we're doing the same kind of thing with permeability. Here we have a low permeability aquifer, a medium permeability, and a high permeability aquifer to look at its effect on the radius of influence. And as you expect, we have much faster propagation in the higher permeability area because it's a function of the airflow, the rate at which you're delivering oxygen to the front. So you can see as the simulation progresses that we get quite different distributions of the front, different rates of cleanup as a function of permeability. So that's not surprising, but it's nice that we can use the model now to sort of explore these issues. And we can do this in, this is a theoretical site, but of course we can also do it for real sites. We can put in the real permeability and real details from these sites and try to optimize the design of remediation technology. So in terms of modeling, what can we say? We've got novel in situ smoldering model developed, can be used for both ex situ and in situ applications. We've calibrated both 1D and 2D lab experiments, and we'd like to go on and we're now going to start doing three-dimensional experiments. So we have three-dimensional propagation. I have a PhD student who's working on that now. We are able to, we've calibrated just to one experiment in the 2D case, but then shown that it can properly reproduce all the other cases. So that gives us confidence that it is working properly. And particularly it's properly simulating the extinction boundary. It's going to be a valuable tool for us for exploring the influence of site and engineering factors, as I mentioned, and hopefully for designing some full-scale field applications. So, like with any remediation technology, you know, we've had to take something over 8 years from early time, it was really just a blue skies idea that maybe NAPL droplets could actually smolder since they're embedded in a porous medium. And you can see we've taken it all the way to in situ and ex situ trials where we have a lot of site owners and regulators and companies that are very excited about taking this to full-scale application. And for most contaminants, particularly the heavy hydrocarbons that it works most effectively on, you know, we're getting the majority being destroyed and very little being emitted. And some of its advantages against other technologies, or some of the places that you want to think about using this is when you have a lot of NAPL, when you have really recalcitrant long-chain hydrocarbon NAPL, when you want to minimize the amount of energy you're using, and you want to either treat soil that was already at the surface or excavate and reintroduce the same treated soil back to the subsurface, or if you want to treat it in place in situ. And this whole project over 8 years is really, and I hope one message you take away from this, is that when you're developing a new technology and you're proving it at all these different scales, that there's a really importance of the collaboration between the granting agencies that give us funding for the research. We have a big team that's collaborating around the world trying to understand and develop this. And, you know, we're trying to develop very fundamental science at the same time as proving things in the field. And these all happen simultaneously. We have consultants that are, linking up with site clients and helping do the site investigation and application, and a really important part of the engineering team. Site owners have to be on board and help take a risk to help you prove this on their site, and also getting the regulators on board that they see that this is a really positive step forward and that they're in favor of supporting these tests. So I want to thank everybody for your attention, and I'll go over here and see if we have any questions. Let's see. Let's see now. We have a couple questions. One question. Can you comment generally on how receptive the various regulators are to STAR? For example, MOE Ontario, EPA, and US. Are you having difficulty getting regulatory approval for in-situ applications? So that's a great question and follows on from my final point here. And in fact, no. A couple of good things. One is that the regulators, like the clients, want to see solutions to these sites. So they're cautious, of course, but they are very supportive of anything that could, especially for sites that have no cleanup solution whatsoever. They're very favorable to at least testing and getting the data they need. For example, so for ours, we agreed that we would collect all of the emissions to see whether collecting emissions would even be necessary. So, they're very supportive of collecting and treating emissions in a standard way that has been used on many of their other sites, so they're very comfortable with activated carbon technology. So, in that sense, they've been very supportive. They want to get the data they need to make a decision, and based on everything that they've seen so far, it looks like it's going to be no problem. For example, this site we've been working with in New Jersey, Environmental Protection Agency, and they have a particular regime for overseeing these sites, and they've been very cooperative and supportive. So that's encouraging. Yeah, so I guess I think that answered that question, I hope. Are you aware of any successful field applications of STAR using horizontal wells? The answer is no. I know of all the field applications, and I've shown them to you. So really, STAR is at the very first stages of that New Jersey site. Is the only I take that back. We've done 2 in-situ pilot trials. They haven't been full scale. They've been pilot scale, which means just one or a couple of wells, of ignition wells. Right, we take a part of the site and test it to show that it could work on the whole site. But one was in Belgium and one was here in New Jersey. And for both of those, we use vertical injection wells. But absolutely, I've been saying from the very beginning that horizontal wells is a very good idea for STAR. It's a very good way to ignite along the base of the contaminated zone, which is, of course, because propagating upwards is the most effective way for delivering STAR, and also is a very effective way to deliver air across a large region. The only difference is that installing horizontal wells is much more expensive than installing vertical wells. So, so that's an issue. You have to compare the cost of how many horizontal wells you would need versus the ease of putting in vertical wells wherever you want them. And in fact, the latest strategy we developed is that we can put in vertical wells as frequently and even during the treatment. If we see a spot that has been missed or that we want to treat again, we can just pop down another ignition point, and we can put ignition points wherever we want, and basically leapfrog them across the site. As we pull out ignition points, we'll go stick them in another part of the site, and therefore just use a couple ignition points to start smoldering reactions right across the site and clean up the site that way. We're hoping that, for example, we could clean up that entire DuPont site in the order of 4 to 6 months, just stepping across the site with basically on the order of 6 to 12 days of reaction happening at each location. So I hope that answers that question. And the third question is, how can I invest in you guys? Well, that's very kind of you to say that. Send me an email. I'll talk to you about it. But basically, my part is to focus on the research, and there's a commercialization company, which is Geosyntec and Serum, and they're the commercialization arm of, and their job is to make STAR happen in the real world, and they're doing a really good job of it. If you visit their website that I gave you earlier on, the STAR commercialization website, there's more contact details about that. I'm sure they'd be happy to hear from anybody who's interested in STAR and any of these. But I just want to say, STAR is not the be-all and end-all, but it is exciting to work on an emerging technology. And I thank everybody for your attention. I hope you found that this lecture was worthwhile. And even if you haven't thought of any questions at the moment, or if you're viewing this at a later time and you want to get in touch with me, please just send me an email. You can obviously use the online forum, which I'll be monitoring, or send me an email. And it would be great to hear from you. All right, thanks everybody. Take care.